Hello everyone, and welcome to today's webinar on metal 3D printing, supporting global readiness for mission-critical applications. My name is Maria Ma, Marketing Campaign Coordinator for Engineering.com, and we're joined by our speakers for today. Welcome, Gary Bredael, Director of Additive Manufacturing for Hartech Group. Gary started out in the early days of SLA and SLS polymer systems when he ran sales and operations for a company called Paramount Industry. Gary currently heads up the AM division at Hartech Group, dealing exclusively with the federal government. Also welcome Luis Vidal, Velo3D's sales director for the Northwestern US, specializing in aerospace and defense applications. Luis focuses on helping customers identify solutions for complex problems using Velo's additive capabilities. He has a background in aerospace engineering with degrees from the University of Michigan and Georgia Tech, as well as an MBA from Harvard Business School. Now, before we get started, we'll first cover a few housekeeping items. Today's webinar will be recorded, then available for on-demand replay on engineering.com. For attending this full live session, you'll receive your PDH certificate within 48 hours. And if you have any questions, please submit directly in your webinar interface, and we'll try to address all questions during Q&A. Now we'd like to kick things off with a poll question. What best describes your reason for joining today's session? You're exploring bringing additive manufacturing technology in-house. You're looking for additional information on Velo3D's end-to-end additive manufacturing solution, or help with a specific part or application, or other. We'll give you a moment to respond. And here are the results. We have a tie with 35% each selecting other or looking for additional information, and 24% selected they're exploring bringing additive manufacturing technology in-house. Thank you so much, participants. And now, without further ado, I'll pass it over to our first speaker. Luis, over to you.
Well, thank you so much, Maria, and thank you very much, everyone, for joining us today. So we'll start off by telling you a little more about who Velo is, what we are, and how we work with customers, and then I'll hand it off to Gary to do the same. So Velo, at its core, we're a metal additive manufacturing technology company. We were founded by Benny Buller, that's his photo, back in 2014. Benny has a background in theoretical physics and spent most of his early career on the silicon side of Silicon Valley here in San Jose, so working for companies like Applied Materials and some solar technology companies. And he really brings what we think of as like a first principles approach to manufacturing, engineering, and also working with customers. We started it as a process company. Our intent was really to do a better job of managing the process that incumbent powder bed systems were deploying at the time. Quickly realized that we simply could not get to where we wanted to be with the hardware that was available at the time. So we ended up becoming a hardware company, and now we produce what we call a full stack solution or an end-to-end manufacturing solution. So we develop our software, our processes, and our equipment, all of our hardware completely in-house, based in San Jose, California, with a fully US-based manufacturing team. Although we do support customers in Europe and in East Asia, so Japan, South Korea, and also Australia. A little more about the type of companies that we work with. So we're predominantly an aerospace and defense company, although we do work extensively with some energy and oil and gas companies, as well as some other companies here and there. Most of who we work with, I would say maybe 50–60% are in the launch space. So we work with a lot of launch companies, both new and old. A lot of the folks that we work with are producing what we call high-value end-use components. So anything really in propulsion systems, thrust chambers, anything regeneratively cooled, different types of impellers, mixers, pre-burners, things of that nature. We also work with a lot of gas turbine companies, both for aviation and also energy generation. We have a network of contract manufacturers that exist within the aerospace and defense supply base that have a variety of broad capabilities, not just additive capabilities, but they're CNC shops. They do a lot of post-processing, heat treatment, etc. And that set of contract manufacturers also works with some of these customers who don't necessarily have systems in-house. So whether you're an OEM or whether you are badge to the DoD and you're in supply depot or your procurement, there's lots of ways to work with Velo. You don't necessarily have to have a system, on site or in-house to get some parts made. And then one quick thing that I'll say is that when you think about what a metal additive part is, one of the things that we try to do as a company is demonstrate, that we're not really just making brackets anymore, right? We're not doing simple things, and we're not necessarily doing rapid prototyping for the sake of doing rapid prototyping. We're really focused on producing, again, what we call high-value end-use components, things that go into propulsion systems, things that manage fluid, things that transfer heat. These are things that are mission-critical parts that absolutely need to have, very high standards of quality, are typically certified either by the FAA, by NASA, or by an equivalent DoD scheme or DoD framework. And they're things that typically have not been done in a production setting with additive before. So again, things like thrust chambers and fuel tanks, and new applications like die casting, which is a new application for us. So I really want to set the stage for our conversation today about the parts that we're talking about. We're not just talking about little gadgets and little brackets and maybe your father's additive part. These are really high value stuff. These are castings. These are things that are mission critical that we're doing with high degrees of quality and consistency. And the last thing that I'll say that might be more of interest maybe to this crowd than to the average is we're a fully US-based company. We were founded in San Jose. We have an entirely US-based engineering team. The vast majority of our supply chain is also US-based, so most of our subcomponents we source from American or at least North American vendors. The things that we do get from Asia, so things like chips, we get predominantly from South Korea, almost entirely from South Korea. And all of our systems are manufactured in Fremont, California, which is just so happens to be across the highway from the Tesla factory, which is kind of cool. So that's all I'll say about Velo. And Gary, on to you.
So have you switched the slide, Louise? There we go. Okay.
I did.
Yep, got it. So Hartech Group, we work exclusively with the federal government, specifically the DoD and a little bit with the DOE. We were born out of a need from the federal government for install and complete turnkey installations. And what I mean by that is I'll give an example. We just put a large gantry CNC mill in at Tinker Air Force Base, and we did all of the concrete work, the electrical, the rigging, and the install of the machine. So when we were finished, it was a complete turnkey. We turned the keys over to the operators. They were trained, the maintenance people were trained, and they were up and running. The bases have a tough time a lot of times generating multiple purchase orders. And the last thing you want is for a machine to show up and just sit there on the loading dock or sit in a warehouse for a year. And that's happened multiple times. So Hartech Group takes care of all that, all of the legwork, the marketing work up front, and the complete installation. We are a woman-owned small business, which helps us with procurement in a lot of situations, not all of them, but certainly some of them. And then we're also a GSA contract holder, MAC IDIQ, and BPA, which is purchase orders for certain bases as well. So it's a little bit about Hartech Group. And then I think we've got a slide next for a question from Maria.
Awesome. Thank you, Gary. So we're going to launch just one more poll question. What are your plans to implement metal additive manufacturing within your organization? You're currently using metal additive manufacturing? 0 to 6 months, 6 to 12, or 12 plus months? We'll give you a moment to respond. And here are the results. We have 53% selected 12 plus months, 37% selected you're currently using metal additive manufacturing, and 11% selected 0 to 6 months. Thank you so much for letting us know. And back to you, Gary.
Okay. So some of the barriers for adopting additive within the DoD that I've experienced in the quite a few years of dealing with the DoD, challenges with making critical parts. It's still it's a welding process. You're adding layer after layer and you're melting it together. There are some challenges and perceptions in the industry that perhaps this technology is not as advanced or not as reliable or dependable as some of the processes that have been there in years past. Louise, did you have something to add on that one or next one?
I mean, yeah, we see it all the time, right? As the tool maker and as the person that kind of goes in first and typically has to deal with some of the skepticism, it's definitely true. I think that additive manufacturing is very much a digital process, and things like casting and forging are frankly very analog processes, and we've been doing them for a long time, a couple thousand years in some cases. So it's very difficult to come in, to a community with something that is just fundamentally a little different than what they've seen before, and not necessarily as easy to sort of internalize, right? It's just not in the water the way that casting and forging is, and machining is.
Right.
I will say that maybe 20 years ago, 15, 20 years ago, that criticism was probably fair, right? The industry was much less mature, but between ourselves and frankly some of our competitors, I think we've done a really good job of, one, producing systems that are simply better than what they were before. And we now have the ability to make parts very consistently with excellent densities, right? We're welding things with higher densities than what you get out of casting, almost universally, with material properties that are between casting and forging. So I think, the perception problem is definitely real, but as they say, the data will set you free, right? And we've been able to demonstrate that we made a lot of progress, and the parts that you're getting out today are not the parts that you were getting 20 years ago.
Yep, no, absolutely. And just in the last 5 years, the amount of progress that's been made has been tremendous. So,
yeah.
And then the next point I had was training of personnel within the DoD. So there's a lot of people here in the U.S. that have a lot of experience with additive manufacturing. The problem is if you try to deploy this technology and you put a machine overseas that's near theater, you may have an operator that's been a soldier, a foot soldier for a couple of years. Now all of a sudden he's got to put powder in a machine and make a part. So
yeah,
you need to have a repeatable, reliable process and something that's very simple for that person overseas near theater to be able to operate. And I think we've come a long way and we've got that now.
Yeah, I think especially in particular for our platform, one of the things that differentiates us a little bit is just the ease of use factor. We designed the system to be a production system that you can put, next to a CNC machine and be operated by a CNC operator. And so the level of education and training that you have to onboard one of these systems is substantially lower than what it is for most of all the other incumbent additive systems. Like you don't have to have a master's in additive engineering or a PhD in metallurgy to be able to operate these things. And we'll get into how exactly that works and why that works, but what it allows you to do is it allows you to kind of democratize, right, the deployment of these things. You can put something down, get someone trained in a few months, and with an adequate support from ourselves and other personnel right within the organization, it's actually quite quick, quite fast to get someone from first pressing a button to getting parts out of it.
Very true. Then certification of parts. So an aircraft, let's say, was built 50 years ago, 40 years ago with certain materials and certain parts. Now somebody has to certify and qualify that new 3D printed additively manufactured part. So it's tough to do. Sometimes it has to go back to the OEM for approval.
Yeah.
Boeing or Lockheed or Northrop sold them as particular aircraft. They may have to approve that part to be able to go on it. So it's a whole process. There are certain levels within different branches of the DoD for qualifying parts to get them on either an aircraft or a vehicle to get that back up and running. So if it's a low risk part and it's not going to harm a person, it's pretty easy to get that part onto an aircraft, and that might be like level 1. Level 2 might be, okay, if that part breaks, it might disable the vehicle, but it's not going to hurt anybody. And then level 3 is, okay, if it's going to break or fail, it's going to hurt somebody. So that's going to need multiple sign-off signatures and certifications to get it on. So they are pushing forward. There are data sets that are being developed within the DoD, and there's a lot of progress being made. Very happy to see what's going on with the U.S. here.
Yeah, I think this is definitely probably the most significant of the problems or the barriers that we've seen so far, particularly in the MRO space, right? If you're talking about maintenance and repair of existing platforms out in the field, this is the biggest thing, right? You kind of go up to, well, the drawing, right, that Boeing and Northrop released has this material with this process called out on it. So how do you go back to the OEM and you say, listen, well, we know this part, this new process is still going to get us the properties that we need, and that's something that we've definitely heard from our customers. And one of the things that we're doing, which we can talk about a little later, is the creation of sort of allowables through MMPDS. MMPDS is an allowable standard. The space industry uses it a lot, and what it allows us to do is say that any part, right, in a particular alloy that's produced on a Sapphire, no matter where that machine is, will come out, right, with properties that fit into this allowable standard. And that allows us to go work with OEM and sort of have that negotiation. It's okay, well, this is not a casting, right, but it's better than the casting, and here's the data to prove that it's better than the casting. And here's the way that we can, and here's the certification framework that we use. And we've had that conversation quite a bit with OEMs and other customers too.
Right, right. I think you're speaking a little bit to the next point of how to de-risk this process, right? So if you've got all of those parameters and material developments and certifications in place with the material in the process, that's starting to de-risk that process. And a little bit more is also getting parts on certain vehicles and aircraft and running them and testing them and validating them and seeing that, hey, this process really does work, and it takes some of that risk away. So post-processing, I mean, you still have to post-process these parts, but for the most part, if you're even near theater, you've got a machine shop with CNC machining centers, wire EDM bandsaws, inspection equipment. So the post-processing considerations of a part are different than certainly a billet stock where you're starting out with a square or rectangular block or a rod stock and a lathe. You've got to locate it. You've got to find the center and then do your machining and inspections after. But it's certainly not insurmountable, and it's being done all the time.
Yeah, it's there's inevitably always some amount of machining that's going to be done to these parts. I think that the folks that tell you can take something out of a printer, right, and put it on an airplane are maybe not being super genuine. But that being said, if you have even a basic set of machining capability, at a base or depot, that's more than typically sufficient, right? If you're machining parts there already, that's all you really need.
Right. And you have the personnel there to do that as well. So we touched a little bit on the OEM approval for the additive parts. At times, you're going to have to go back to that OEM to get approval. I think some of those approvals may be very rapid or overlooked if we're ever in theater and we need that part quickly. But right now, at the base level, when we're doing repairs and so forth, you're going to have to get that approval in a lot of cases. Yeah. And then it really.
Oh, sorry, Gary.
Go ahead.
Well, no, I was going to say that it really helps when you have, the folks that you can lean on that essentially spend their entire time, right, talking to these types of companies and talking the language and talking to engineers. A lot of the applications engineers that we have, and a lot of the folks on the sales team, including myself, works for one of the, large defense primes, or at least have some experience, with working with engine companies or with aerospace companies. So it's a language that's definitely embedded, right, in who we have, right, as people. Right,
absolutely. And we did touch already on the perception that the EM part is not good enough. We talked about materials being manufactured via castings years ago, and if they're starting to do some CT scans on some of these castings, and they're just floored at the amount of porosity that's inside of these castings. And when you do a CT scan on an additively manufactured powder bed part, you might see tiny little microns here and there that aren't 100% sintered, but it is nowhere what a casting is. So the part integrity is there. When we're 99.9% dense, we've got some great parts and great stories to tell.
Yeah, that's like the most frustrating part of my job. It's like you get compared to castings, right? Or not necessarily compared to castings, but they talk about you with a certain degree of skepticism, but it's like, you guys have been casting this thing for like 50 years, and that casting is, not particularly very good. So just dispelling a lot of myths is a big part of the job.
Correct. Yep. Let's take a look at the next slide.
Right, next slide.
So opportunities, there are a ton of opportunities within the DoD, and they are doing a great job of pushing this technology forward and trying to deploy it and get it involved in as many applications as possible. So deployment of AM locally in the US, they're doing a great job. I don't think there's a base in the US anymore that doesn't have some form of additive, whether it's polymer or metals or both, and they're training the personnel here. They're getting them up to speed. People know the advantages of it and what it can do for them. And then DoD working on AM deployment abroad. So there's a lot of Connex boxes where they're making deployable assets. The Navy just put it's actually 2 different 3D metal printers on ships in the last couple of months, where they put them inside of a Connex box, raised them up, basically plugged that Connex box on and started making parts. So deployment of the technologies is there. Powder bed is probably not going to happen for a little bit yet for real near theater deployment because of the powders and the process that's involved. Some of these other ones are wire fed technologies or polymer technologies, but it's there.
Yeah, powder bed, which is all that we really do, is I think the application for like very near theater is not quite there yet, just because of the operational complexities of the system. But when you talk about like depots having spare, like MRO applications, or where you need to get a spare out, and that spare might have been a casting, and God knows, right, what that supply chain is like here in the States or somewhere else. That use case is like, kind of hitting the nail on the head when it comes to good use cases for powder bed fusion.
Yeah, just for everybody's, most people know this, but near theater means not where you're fighting the battle, but off the battlefield. But normally there'll be a large hangar, warehouse, whatever, with equipment, machining capabilities, fabrication equipment inside. So that's what we're talking about for near theater. Then the rapid approval process, we did touch on that a little bit on the first slide. There's different levels within the DoD and different branches, Army, Navy, Air Force, Marines, all have their levels of approval to get an additive part on. They're ramping that approval up in a lot of cases because they're having success stories. They see what an AM part can do for them. So I'm very happy to see that the AM is pushing forward and moving as quickly as possible within the DoD.
Yeah, definitely. All right, so we're going to move into a couple slides here where I'll just take the conversation that Gary and I just had and kind of retell it in the framework of Velo. So we got a few problems and we have quite a few opportunities. And how does Velo address some of these problems, right? And how can we address some of these opportunities? And I think we're taking questions as we go along. And so if you do have questions, feel free to ask them. And I believe that Maria will, kind of help us with a Q&A session towards the end of it. So, and then if you don't get a question answered, there'll be some emails at the end of this where you can reach out to Gary and myself. Very happy to have conversations offline too.
Absolutely.
So we talked about, Velo as a metal additive manufacturing technology company. And we talked about kind of this whole full stack, quote unquote, solution. And that is really comprised of 3, maybe 4, depending on how you think about it, different things. One is our preprint software called Flow, which we'll talk about here in a second. One is the system itself, which is the tool, the printer, the Sapphire. And the last is Assure, which is our quality validation management software. Both work in conjunction together. So when you work with Velo on a Sapphire, you work with all 3 of these products at the same time. Whether you own the system or whether you went to a contract manufacturer that ran the system, it all comes together. And then underlying all of those things is the manufacturing process, which is the really critical element of this, right? When you're in the Velo ecosystem, you're you're guaranteed to be running the exact same manufacturing process, no matter where you are or where you go. And that's very different than what we call incumbent additive today, right? If you go to one service bureau or one machine somewhere versus somewhere else, what that machine is running in terms of parameters could be very different than what the other one's running. You get very different results, even if the machine is the same. So talk about that a little bit as well. We'll talk.
Yeah, Louise, that speaks volumes to what we spoke about having an operator near theater. There's a lot of operators here in the U.S. that have 20 years experience and really know how to operate a machine. That person near theater is probably not going to have that experience. So this software is just a great additive for us. Yeah,
and Flow is the entry point, right, for your model. So you'll take a CAD, and the great thing about Flow is that it reads native CAD. It doesn't take STL files. We kind of made a conscious decision not to read STL files pretty early in the development of the software. So it allows you to take a file that is typically more readily available, and you don't have to do any translation to it. What it also does is it allows you to keep geometric definition, right? So like all the surfaces and things like that are retained once you import things into Flow. And what that allows us to do is it allows us to intelligently identify certain types of features, right? So Flow can tell what a low angle surface is, right? What a thin wall closure is, what a peninsula might be, what bolt core might be. And all of these different geometries want different things. If you think about what is the laser doing specifically, going into it a little bit, like what's the rastering pattern, what's the power, what's the focal point, how fast is it going, how are you dealing with edges, right, and corners. All of those things will be different for different types of geometries, right? So in order to maximize your chances, right, of success for a particular part, you want to deploy the process that's going to do what the metal and that particular point wants it to do, right? And that's why Flow is so phenomenal and why it's so easy to use, because it'll read this and it'll essentially make intelligent allocations itself, right? So, okay, well, this is core here, this is the wall here. As the user, you can always override that and sort of tell it what to do when you want to do that. But on its own, right, it does a very good job of deterministically allocating a particular type of sub recipe, right, which is a big part of that, like first part quality. There's just a lot less parameter development. There is no parameter development, frankly, and very few iterations you have to go from like one part, a test part, the first article, to something that's successful. And the other thing that I'll say is that we have a growing library of these sub recipes. So every time we have a customer that comes to us and says, hey, your processes are not really resolving this particular geometry very well, can you help us? We'll go in, we'll develop a process for that. We don't charge for any of it, and we just load it back into Flow and we push it back out, and that way the product gets better. And so every feature that we have because someone's come to us and said, hey, you should do this, or it's not working on its own. So that's Flow. And then we move into the Sapphire family of printers. So we've got two platforms, the smaller Sapphire, which is a 315 millimeter diameter build plate, and the larger Sapphire XC, which has a 600 millimeter diameter build plate. And I say the word family, and I use the word family for a very good reason, and that is that all of the parameters, the processes that are run in one system are shared across all of them. So the laser instructions for a particular recipe, what we just talked about before, are the same. The only thing that's different is laser scheduling and how lasers are allocated to specific parts of the build plate. But what the laser is doing at a particular point in time for a particular geometry is identical. And that gives you really great scalability, right? You can develop something on a small Sapphire, and then when you have large enough quantities, you can upgrade to an XC or work with a contract manufacturer that has an XC and get production level quantities made much more cost effectively than you can on the smaller system. The smaller Sapphire has two 1 kilowatt lasers, and that 1 kilowatt is fully usable, and the larger XC has 8 kilowatt lasers. It's argon, positive pressure environment, 50 micron standard layer thickness, which again goes back to the standardization of this process. And then the calibration question is also incredibly important, right? So for a lot of incumbent systems, to calibrate the lasers it is a very manual process, right? And it's just something that takes either a skilled operator or someone from that company to go in and do. And when you're talking about, not even near theater, right? But if you have, like operations on base, it frankly can be really challenging, right, to get folks in there. And then also, it makes producing quality parts on a recurring basis very difficult if you can't get things calibrated on a consistent basis. So our system has what marketing calls like a one-touch calibration. It's actually five little things you have to go through. But it's something that, again, the operator can do. You don't have to kind of go in there. You don't have to have a skilled operator to do it. It's literally something you press on the screen and it calibrates itself.
Huge differentiator for us, which is great for our guys.
Yeah, we hear really good things about this capability all the time, right? Especially if you have experience with incumbent systems. It's just so much less, right, of a headache to get these calibrated. And then the last thing that I'll say about our system is that we take in situ monitoring very seriously. We have almost 1,000, it's closer to around the mid-900s sensors between synthetic and actual physical sensors that are measuring things all across the system constantly. And we push all of that data to Assure, which we'll talk about on the next slide, to make sure that the process is being run within the process window. And that goes back to, how do you know that you're getting a good part, right? Okay, so you printed this thing and this machine, did this. How do I actually know that what was done is what I wanted to happen? And that's where Assure is such a big differentiator for us. It comes again with the system. It reads data off of those sensors and off of a tool called Height Mapper. Height Mapper is just a structured light scanner. It's a laser that sits at the top of the build chamber, and then it scans the build bed, before and after recoat, and then after the laser, every single layer. So it takes that data. It also takes process monitoring data. So we look at, peak height. We look at oxygen content. We look at delta pressure in the filters. We look at the whole argon. We look at a whole bunch of things. And then we publish all this data in what we call build reports that are like anywhere from like 3 to 5 page reports that will very quickly and succinctly and in a very actionable way tell the operator whether or not the machine was calibrated and in spec, and whether you're getting something quality, and whether you're getting the quality out of it that you expected to. And again, it's a big differentiator. There are other sort of third-party softwares and tools that you can get and integrate, but because this is integrated into the product from the beginning, and they talk to each other very seamlessly, we feel like just the ease of use and the quality and the consistency that you get out of stuff in Assure is great. And then also all of this stuff sits on-prem. I just want to be very clear about that. So we don't see any of this data, right? This sits on a little box that sits next to the machine. It's not connected to the internet. Velo, our operators have no ability to look into this. So when you talk about like OPSEC, there is no, you don't have to be connected to the cloud. There's none of that nonsense, right? Like all this can be done on a computer that sits right next to the machine. It's really quite, we take that very seriously. And we have customers that have these machines operating in secure facilities. We'll have hopefully machine operating in a facility with security clearance early next year. So OPSEC is something that we take very seriously.
Yeah, it's good point, because there's a lot of facilities within the DoD, Luis, where you're not going to be able to hook up to the internet. So thanks for mentioning that.
Yeah. I mean, it's a huge deal, and I know that there are a couple like polymer companies out there that have had for a long time this cloud-based software you have to connect to, and it's just like, I can't do that. It's just no. So let's talk about alloys and materials. So we try and be really responsive to the market in terms of what people want for alloys. Every alloy that you see here has been requested specifically by a customer for a specific application. So if there's nothing that if you don't see what you need, maybe like stainless could be one of those. There's a good chance that we're either already working on it or that we can do it for you given the application. And again, we don't charge for material development, specific material development. Most of the alloys, as you can tell, are really geared towards the industries that we work in. We do a lot of super alloys, a lot of nickel super alloys, Inconels, got some Hastelloys. We've got titanium and aluminum are pretty standard. We do copper. GRCOP 42 has one application application. It's an acid copper used for thrust chambers, and that's kind of rapidly becoming one of our most popular alloys. And then we just did tool steel. We're really excited about M300. We're looking at predominantly automotive die casting applications. So if you have, these tool inserts that have cooling channels in them, you want those cooling channels to be as large as possible and also as smooth and good as possible. And we've seen some pretty good distinguishing capabilities on our system over others for tool steel. And that allows you to do, other types of applications, so not just die cast inserts. We are working on an alternative to GR-COP 42, which is a little less expensive and more available. Stainless, we've got a couple of stainless steels that we're working on, and also considering a couple of new as well. So if you don't see the alloy that you need, that's okay. Come talk to us. There's a good chance that we're either working on it or we can get it for you. And then this slide, I want to really emphasize the point here. And the point here is that we as a company, Velo as a company, tend to be incredibly committed, frankly, maybe too committed to our customers, right? I mean, we will work with you and bend over backwards to get you guys to print and execute things you need to print. And we will be in the room until you tell us to leave. So, we call it the Velo Bear Hug, right? Whether it's application support, process support, like sales and business development support, we really like our customers to think of us as an extension of our team. The customers that we work the best with are the ones that have, found a way to bring us into the fold, really seriously. And we really value those relationships. And really what we want to do, right, what we're motivated to do, incentivized to do as a commercial team and as a technology team, is to make people successful. That's how we measure, right, success.
Right.
So when it comes to understanding how to slice parts, understanding, any development that has to be done, working with OEMs, which we already have relationships with all of the major OEMs, talking to engineers, talking to people in certification agencies like NASA and the FAA. We might not necessarily be able to do a lot of that for you, but at the very least, what we can do, we will. And what we can't do, we can definitely sort of like help you based on our prior expertise to point you in the right direction.
And Luis, just to add to that, we have a network also of suppliers, and a lot of those are ITAR certified as well for the DoD if we need to make parts there. Yeah.
That's I'll stay on this slide, but yeah, I mean that's another really good point. I mentioned earlier that you don't have to buy a sapphire to get parts made on a sapphire, and that's this point, which is that we have a network of ITAR certified AS9100, ISO 9001 suppliers that are all in North America, already do work for the aerospace and defense industry, probably are already certified suppliers, maybe in a couple of cases, and we work very, very closely with them to make sure that parts are successful. Right, like when we consider all the certification things that we need to consider, that we think about material properties and post-processing. So no matter how you get a part made on a sapphire, we will be there to help to the degree that we're needed. And our contract manufacturers are very skilled and capable in producing parts, not just printing parts, but also machining parts, heat treatment, post-processing, assembly if required, things like that. And what I'll mention about, so kind of moving into this like golden build file, I mentioned a few things earlier that I'm going to tie together. One is the standard process, right? So there's every sapphire is running the exact same manufacturing process as every other sapphire. Every sapphire has a standard calibration routine, which allows machines to be calibrated on a weekly basis, right? Or almost, before every build, depending on how long that build is going to be. And it's all been designed in-house. So everything that we've done, has been designed to be integrated, right? It's an integrated product. But that has allowed us to do is develop what we call these golden build files. A golden build file is one file to rule them all that can be run on any system and produce the exact same results no matter where you are. And the real magic of this, particular for like DoD MRO applications, is that you don't have to now be in a position where you are reslicing or managing files, dealing with STLs, and dealing with different machines in different calibration states. That doesn't have to happen anymore. Like today, it is a nightmare. Like if you have, a couple different machines, and those machines in 2 years might be in a different calibration system, or before, there's a chance you're probably going to have to reslice that. And there's a lot less certainty that what you're going to get is what you expect. And because none of that is really true on the Sapphire, you get one thing, one build file, whether you want it today or in 2 years or in 5 years, no matter what software version that system is running, it's going to run the same parameters, right? Because the parameters are embedded in the file itself, which is a massive differentiator. Everyone else will take essentially what is like a tessellation, they'll load it into the machine, and then the machine will say, all right, I want to deploy these parameters in this way on this layer. So the files are bigger, but the benefit is there's one file, right? And so if you're working off of like a central repository of approved files for particular parts, that's one file. So whether you are, like operating a vehicle and you need something printed in Germany or at a base in the States or, at a base in Japan, it doesn't matter because it's the same file and you're literally pulling the same file. So huge, massive differentiator. And then we'll talk a little bit about qualification. And this is obviously a huge topic, so I won't kind of go into it too much in this forum, but very happy to answer questions after the fact. We think about qualification in kind of 3 different steps, right? Or in 3 different phases. One is material qualification. So what are the properties that you're going to get out of this material? Tensile properties, elongation, cryo properties, whatever it might be. And we're doing that through standards. So MMPDS and NACE are the 2 that we're working with today. The goal is to have all of our alloys. We're currently closing up on 718, although that data has not been published yet. And what that allows a customer to do is it allows you to call out MMPDS standard X, Y, and Z, right, Inconel 718. And you put that on your drawing, and that's going to reference a set of properties that you can then call out. And again, because the processes are the same on all the machines, I'll say this a million times, you're going to get the same properties, and the properties will be within the same family. And then you go into Sapphire qualification. So when you land a machine, there's a set of qualification builds that you have to print. We have a standard set of builds, and typically customers will have their own builds that we'll do. And that drives machine consistency, so that we know that this particular machine has been calibrated, all the systems are working together and talking together nicely, everything's working as expected. And when we run this particular parameter on this particular type of part, we're going to get the same properties, and we're going to get the same result. So when you land the machine, you'll typically go through a qualification process to make sure that what you're getting is within the family of the allowables that you've published, the MMPDS allowables. And then you go into part qualification. And this can depend greatly on the certification regime that you're living under. But what you'll typically do is you'll go through, you'll print a couple parts, you'll print a couple coupons with those parts, and you go through some sort of like testing regime to prove that the part can do what you said it can do. And then you lock that file down into your golden build file right after you get part qualification. You load that into your database and say, all right, this is the file for the qualified Gizmo A, right? And anytime you want to print Gizmo A, you use that file, and that file is going to be guaranteed to run the same process that you qualified this part to, right? You qualified it. So again, massive differentiator and really significant part. And if you're an OEM, for example, you can now take this part, you can take this print file, and you can load it into your PLM software, right? You can say, okay, this is my release drawing, and you can attach this build file to that drawing file. And so when supplier management wants to go off and acquire, X quantity of these parts, it's there. It's no different than sending a drawing out to a CNC shop to get it CNC. You don't have to finagle with properties or who's the vendor or what process are they running. Is it the same as the process this other guy was running? Is the process the same as 2 years ago, right? All those things are just no longer relevant questions. And so even from like a supplier management perspective, whether you're kind of batch DoD or you work for an OEM supporting a DoD customer, it just really makes things a lot easier. And then we can talk about a couple of real world examples. This will be pretty casual. We have a lot of customers that maybe do a better job of marketing us than we do. Launchers. Launcher is one of those. The launcher has a couple of our systems, and we have a really phenomenal working relationship with them. So their E2 engine has quite a few components that are printed on our system. They print components on a competitor system too, but a lot of the volutes, particularly the geometries that you see at the bottom of that stack, are printed on our system. This will be launched in 2024, so it hasn't flown yet, but I think it's the highest performing Carolux engine ever been designed. We have a lot of components, both static and rotating. We do rotating components. Some people tend to shy away from that for additive parts. We've seen a lot of success with rotating turbo machinery.
And Louise, just to reiterate a point you made earlier, these are production parts, and they're complicated production parts. So it's not just for prototyping. These are flight ready, flight critical parts.
Yep. Launcher is going to be certifying this engine with NASA the same way that all of our other launch customers certify the engines that they're making with NASA for unmanned and manned spaceflight. And these are production parts. So it's not like they're going to make a prototype and then they're going to cast all these things in production. It's like, no, their plan is to print these things forever, right? That's the production solution.
Yep.
And the other benefit, I'll kind of piggyback on this particular slide, is that a launcher can have a couple systems in house, but they might not necessarily want to scale production entirely. I'm not saying that this is true about launcher. We use this as an example. We do have customers that they do have systems in house, but they also source from the network, the contract manufacturing network. So they can do development and low rate production in house, but they don't necessarily want to dedicate the money that it requires to invest in the capital. And so, okay, instead, I just want to buy like 10 parts per month, and they'll work with the contract manufacturing network. And because they already have a system and they've qualified the part themselves, they own the build file. It's their IP. And they send that file out to 2 or 3 different CMs with the alloy that they need. And there's no overhead. It's just you put it in there, you calibrate the machine, and you click go, right? And you're going to get the property that you expect to get because the process is the same. Hammer that nail again. It really gives flexibility. I think the thing that I want to really sort of embed in people's heads here is the flexibility, right? Like, yes, you can have a system in house, but because it's been designed fundamentally differently than how our competitors are designed, you have the flexibility to rely on a dynamic and flexible and competitive manufacturing network, right? Like all these guys, all these people that run these manufacturers are competitive, right? And in the same way that you would send a part to get CNC'd on a DMG Mori 5-axis to like 4 different people that run the same machine, it's the same scenario here, right? So it's really trying to kind of push the paradigm, right, of metal additive production from one that is dominated by people that kind of control your relationship to one where you have a little more leverage to work with people you want. This is another really interesting example. So again, leaning on the whole supply chain flexibility question here. So we developed a flow control valve or a choke valve for IMI. And IMI is one of these like global oil and gas companies, and they don't necessarily want to stock a ton of spares, but they also want to use the technology to get some added performance that they can get on these flow control valves. But there's a lot of really critical channels in here. They're very small, and you need to know that the process you're running in these small channels is going to be consistent, because if you're not consistent and you get defects or you get blockages, things that can happen with really small, delicate geometry, that essentially defuncts, right, the use of the part. So we help them produce this part, and they're going to be deploying this across a network of contract manufacturers and systems globally, both in the United States and Europe at this point in time. So really great use case. Again, really but kind of leaning on the supply chain flexibility that we provide, as well as the geometric capability, which is still like a foundational part of what we do, which we actually haven't talked about much today. Maybe we can talk a little bit about that on this part. One of the things that is also differentiator for us is our geometric flexibility. Like there are parts that you can make on our system that are physically impossible to make on other laser powder bed systems. And that is not an exaggeration, right? So we can do, there's a rule of thumb, which you might have heard of in metal additive, which is 45 degrees. You can't go below 45 degrees. There are certain exceptions, and I think people have proved out some of those exceptions elsewhere. But what we like to say is that, you can go down to, near 0 degrees as long as you're adequately constrained in certain ways. And what that allows you to do is print overhangs that are way lower than 40 degrees and accomplish parts that would be too challenging to make because you have to support them. And this is a good example of that. There's a flange on the inside of this housing, which is, I think it was like 10 or 15 degrees. There's a couple other low angle overhangs at the bottom of this housing, which are also between 10 and 20 degrees. And there are other parts that have lower overhangs as well, especially shroud impellers, that we can now do. And so this is a use case, Siemens Energy. I can't disclose the engine that this is on, but I can say it's a power generation system. This is a real part. It's 60 different parts between casting, a CNC machine, sheet metal that's been welded, and we consolidated all those parts into one. And they'll be printing this, right, for production systems and for MRO spares on power generation system.
Big point too, Louise, is printing these low overhangs with no support. If you're printing these internally, you may not have access to breakaway supports like the other systems. They're going to populate them and say, oh, we just get the supports out. Well, you may not have access to them. So with our process, you don't need the access because they're not going to be there.
I'll go back to this part. So if you take a look at this volute here, kind of towards maybe quarter of the way down, or quarter of the way at the bottom, this is a fairly sizable internal volume, right? So this is a volute that's hollow in the middle. In a lot of systems, you would have to either support some of that geometry, and at some point in time, supporting geometry is okay, but at some point it just becomes impractical because you can't get to it. So especially with propulsion components, and other things that you would have cast, typically you're going to cast something because there's an internal cavity somewhere. Going direct from a casting to an additive part sometimes is very challenging because you're left with these overhangs, which are not a problem in casting. Not sometimes they are, but usually they're not. To now, okay, well, I've got this overhang, but now I have to support it. But it's this internal channel, and I can't get to it anymore. So that's the challenge. In our system, a couple things that I haven't talked about allow us to do this. We can do internal overhangs without support structure, so that you can have a much easier time going from a casting, not changing that, right, and going direct to the machine, to the printer, and getting something that is a better facsimile of that casting without having to deal with all this internal support structure. Yeah. Did you have anything to say to that, Barry? I'm trying to get it.
No, I think it's an extremely valid point because post-processing is an issue, certainly for anybody here doing production. But if you can eliminate that for a foot soldier that's being deployed, it's a big factor, and less chance that you're going to have a part that's destroyed because somebody ground away the wrong piece or ground too deep into a part and then destroyed it. So yeah, I mean that's the thing that we are up against all the time, right? Which is, the industry has told us, right? The industry tells you, right? Oh, you can do whatever you want, except this and that and this and that and this, right? And there are legitimate physics-based reasons for why a lot of those things cannot happen, and there's certainly things that we can't do either. But philosophically, our goal as a company, right, was to allow people to make the part they want to make, not the part that they can make, right? So it's a lot of that designed for additive manufacturing.
Yeah, we have this whole, death to DFAM, slogan. I don't think it's caught on, but I think the message is that we want you to bring the part that you want to make and not have to make compromises to get it done. Right. And there are typically the customers that come to us because of this reason first. Right? It's I got to make this part. It's got to be this way. I can't not have it this way. And then they realize that there are all of these supply chain benefits. And then it just makes the cake even sweeter, right? Because it's they get the cake, they get to have their cake, and eat it too. I get to make the part that I want to make. I don't have to make the compromises I want to make. And also, it's just a way easier, right, story to sell to supply chain.
Right.
There's a lot of benefits all around.
Yep. Yeah. Agreed.
And that's all we have in terms of formal slides. And thank you for those of you who stuck around and are still here. I think, Maria, if you want to help us out with Q&A, very happy to take questions now.
Yes.
Wonderful. Thank you, Luis. Thank you, Gary. Here's our first question. What are the current main limitations, if any, of metal additive technology, and how do you see the future of this manufacturing technology?
That's a good question. I can take a whack at it, and maybe Gary, if you want to add anything, you can add something. A couple limitations. One, I think quantities are definitely a challenge for us. If you're in very, very large quantities, it's typically not, additive is typically not going to be the best solution for you. So if you're talking about what we call like aerospace quantities, right, in the tens to thousands a year, that's a good spot for you. If you're in like automotive quantities, like tens of thousands, hundreds of thousands of parts a year, we're not going to be very cost competitive with something like casting. So if the quantities are that level, it's probably not going to be the right solution because it's going to be too expensive. That's one thing. I think there are still some challenges with geometries, right? That you might not be able to do. There's certain things that we just can't violate physics, not too much at least. And so there's certain geometries that sometimes come across our desk as like, we can't necessarily do that. And then maybe the last thing that I'll say is just the perception, right? I think that we have done a lot to improve, right, what you're getting off of our systems, both in quality and consistency. Like you are getting fully dense metal, your properties are going to be better than castings across the board. They're going to approach forgings, but they're going to get some knockdowns and things like petite and forgings. They're going to be better than casting, right? And then proving to people, right, that don't have the experience that, yeah, this is a process you can trust. You can have like the operational scheme in place to make sure that you're operating the machines in the appropriate way. You have the right checks and balances to make sure that if something is out of spec, you can catch it, right? There are other non-destructive testing techniques that you can deploy to deal with some of these things. So I think just bringing additive as a technology kind of out of the prototyping regime and into the production regime, and proving to people that this is ready, right, for game time. It's not something that you're just going to be making widgets on and then doing it, doing the rest of the machining. This is ready, right? I think the biggest challenge for the industry, not just for us, but the whole industry, is determining or showing people, right, that we're there.
There's also a cost barrier for entry, right? So these machines are not inexpensive, but I think to your point earlier that you mentioned, Louise, is that there's a network of people out there that you can get started without buying a piece of equipment and start validating. So I think cost is still a barrier for smaller companies that want to get into the metal 3D printing arena, but there's ways around that to get into it.
Yeah, the systems they're not cheap. They're definitely more expensive than like your equivalently volumed CNC machine. That's right. For sure. I think as technology matures, it will get less expensive over time.
Absolutely.
As bigger machines come into the market, like per part costs will go down over time. And then the last thing that I'll say on the technology side is surface quality. So it is a welding process. Because it's a welding process, you're just not going to get mirror finishes. And sometimes you get customers that come in and expect to get like a machine finish, and that just is not the case. It's not going to be the case for us or anyone else doing powder bed fusion. So if you're looking for like mirror finishes or applications that require mirror finishes, just understand there's going to be some post-processing required to get there.
Yeah, I think the trade-off is complexity, right? When you're looking at a rocket engine, your surface finish may not be perfect on the outside, but you can combine 50 pieces into one. So there's a lot of advantages to it as well. So
Awesome, thank you. Next question: any breakthrough to share in respect of thread making within metal additive manufacturing?
Thread making, assuming that you mean like screw threads, threading. If that is what the question was. I think what we say is that if you need functioning threads, at least on our system, we typically suggest you machine those after the fact. You can do threads. But again, back to the surface quality problem, typically, there's a certain surface finish and smoothness that you really need for effective threads or functional threads that you're just not going to get off of a powder bed system, ours or anyone else's for that matter. So if you need a functioning thread, like a mechanically relevant thread, then you should probably post machine that.
Yeah, and that post processing is quick. If you grow the pilot hole, which is undersized, very easy to just run that tap through there and get a perfect thread on the part. So
yeah.
Chances are you're going to do some post processing on that part anyways, on anybody's system. And once it's in that CNC, you drop the tap in there, you hit it, and you're done. So it's a quick threading process.
Yeah.
Great, thank you. Does Velo3D's integrated end-to-end system of design, build, automated calibration, and real-time quality/process monitoring also provide diagnostics to aid users in the correction of an out-of-specification condition at any point along the way?
Wow, very thorough question.
I'll let you take that one, Luis.
Yeah, I'll take that one. That's a great question. So yes, with an asterisk. So we do, while we do collect height map or an image data while it's printing, so you can go into Assure as your build is going on and you can look at every layer image, and if it detects a protrusion or if it detects some anomaly, you can go in there and you say, okay, well, what does this particular layer look like? So you do have that ability. Aside from that, sort of like in situ, we don't have anything developed yet. We do have a surface defect tool that you can deploy after the fact. So once you're done, you can take that data and you can run it through our defect analysis software, which I believe we're going to release at the end of this year, I think is the goal. And what that'll allow you to do is deterministically determine where there are melt-pool defects on low-angle surfaces. So if you have like an internal cavity or like an internal ceiling, like a shrouded impeller, and you can't necessarily get in there and inspect it where you are, you can use that tool, and based on what it has seen in the print, it will tell you with a certain degree of confidence whether or not you're going to have defects and where those defects will be. So you'll get like a little image and you'll see little red dots. Those red dots are going to be where those defects are. We're still working on being able to use data to determine bulk defects. That's a little more challenging, like core defects as opposed to surface defects. It is something that we're working on, though. Hopefully that answers the question. And you could feel free to email me after the fact too if that didn't get it for you.
Awesome, thank you. Next question, what would be the minimal gap in case one tries to 3D print metal mesh, i.e. aluminum?
Good question. Couple rules of thumb that I'm allowed to say, and then all of this is kind of asterisked with, it is really dependent on your geometry and what you're trying to accomplish. And there's kind of like two regimes, right? There's the regime where you're looking at a lattice, and that lattice has like physically defined members like in CAD. And there's another regime where you have kind of like a porous media that you're trying to make, and that media is not determined by physical model, it's determined by your process parameters, right? So both of those things you can do. I know that our negative feature size, so if you have like just like a vertical hole, right, the thinnest that you can go down is 500, 600 microns, and that's the same for horizontal holes. Horizontal holes might be a little bigger than 500, 600 microns, closer to 700. So that's like a small negative space, like a hole, right? That can be defined that you can have. And positive features, so like physical features, I think you can go down to in aluminum. I believe it's 350 microns to 400 microns leak tight. So if you want to make sure that it's like again fully dense material, 350 to 400 microns for vertical walls. And it depends on your geometry too, right? If you have just a wall that's cantilevered down to like 15, 10 degrees, that thickness will go up as the further you go down. We can do porous material at thinner than that, so down to 200, right? 250 microns, you can do porous material, and that'll kind of look like Swiss cheese. If it's a wall, it'll kind of look like Swiss cheese. And then that's for like defined features. If you have like a parameter set that you've developed to give you a porous material that looks like a sponge, that I can't really answer off the top of my head. That takes some development work, and we've done that with some customers. Unfortunately, it tends to be on a case-by-case basis, and something that you would have to reach out to us and get an NDA, and we can talk to you more about what we can do there.
Awesome, thank you. So I do see we are over our time, so if it's okay, we'll just ask a couple more questions to finish it off. So this next one, what is currently the biggest form factor for metal additive manufacturing? Let's forget about bridges.
Our biggest form factor is 600 millimeters by 1 meter, 600 millimeters in diameter by one meter tall.
Right.
But I think there are other systems out there that might be larger in form factor, but that's ours.
Yeah, I think if they're building a bridge, they're probably using wire DED, where they're just continuously feeding wire and building that bridge. So it's a completely different process than metal powder bed that we're talking about.
Great, perfect, thank you. And just quickly, we'll do one last one. Any breakthrough in multiple metal print in the same setup? Any benchmarks for this?
That's an interesting question. There are people that have done it. It is very challenging. We have not. We've been asked about it before. We don't really have plans to do multi-metal printing. The challenge that we've seen is, it's not that difficult, right? To like lay one layer of one metal and then lay another layer of another metal and then kind of do that back and forth. That's not that physically challenging to do. The challenge is to deal with contamination, like interlayer contamination, and then also what you do with the powder. Because now you've got this like volume of like, I don't know, 2 different powders, and what are you gonna do with it, right? Are you gonna send it back to a vendor to recycle it? Are you gonna separate the powders out yourself? Are you gonna dump it, right? If you dump it, it becomes an extraordinarily expensive proposition. So there are some folks kind of doing niche applications for that. We haven't seen any real production solutions for multi-metal printing yet. Maybe it'll get there at some point.
I think if you're doing multi-metal printing, Louise, there are DED, powder-fed DED applications that you can do it very easily because you just feed a different powder into the system. And they have 3-5 different powders that you can start blending in. And you don't have to worry about contamination because whatever blows over, you just throw it out. But metal powder bed, I don't know of anybody that's doing it.
Yeah, that's a good point. DED is a lot easier. I know I think there's like 1 or 2 companies, like very niche companies doing multi-metal printing. I don't know who they are. I just know that there are people that are doing it.
Good.
Awesome, thank you so much. Well, that concludes our webinar for today. Thank you again, Gary and Louise, for a great session, and thank you attendees for joining us. We hope to see you all again for future webinars. Bye for now.
Thank you.
Thanks so much.
All right, bye-bye.